Have you ever wondered if even the most ideal electronic components have hidden factors that can surprisingly impact their performance, especially at higher frequencies? It turns out that, even in carefully designed circuits, subtle elements can introduce unexpected limitations. Let us explore one such critical aspect in operational amplifier circuits. Yes, parasitic capacitance absolutely limits the bandwidth of an inverting amplifier. This unintended capacitance, present in every real-world circuit, acts as a low-pass filter in conjunction with the circuit's resistances, ultimately rolling off the amplifier's gain at higher frequencies. The primary mechanism for this limitation involves the input capacitance of the operational amplifier itself, along with stray capacitance between circuit traces and component leads. In an inverting amplifier configuration, this parasitic capacitance appears across the feedback resistor or between the input and ground. At higher frequencies, the impedance of these parasitic capacitors decreases, effectively shunting the feedback path or loading the input, which causes the gain to drop. This phenomenon is a direct consequence of the frequency-dependent behavior of capacitors, where their opposition to alternating current diminishes as frequency increases. To address this, engineers often employ several design strategies. One common approach is to use a small compensation capacitor in parallel with the feedback resistor, intentionally creating a lead network that helps offset the pole introduced by parasitic effects. Another technique involves careful board layout, minimizing trace lengths and separating high-impedance nodes to reduce stray capacitance. Choosing operational amplifiers with lower input capacitance is also a fundamental step in high-frequency design. Understanding this limitation reveals the importance of the gain bandwidth product, a fundamental specification of an operational amplifier. This product tells us that, as you increase the closed-loop gain, the usable bandwidth inherently decreases. Therefore, for high-gain applications requiring wide bandwidth, a higher gain bandwidth product operational amplifier is essential, ensuring the amplifier can maintain its intended gain across the desired frequency range despite parasitic effects. This highlights the delicate balance between gain and speed in real-world op-amp circuits. Ultimately, recognizing and mitigating the effects of parasitic capacitance is key to designing stable and predictable inverting amplifiers, especially in applications where high-frequency performance is critical. By carefully selecting components and optimizing layout, you can ensure your amplifier performs as intended, delivering precise amplification across the necessary bandwidth and preventing unexpected signal attenuation.